Okay, good afternoon, everyone. Welcome to our Ezra's Roundtable System Seminar today. It's my great pleasure to introduce our speaker. It's Dr. Scott Pakin. So Scott is a scientist in Los Alamos National Lab. He has been there for almost 20 years. He's one of the recognized research leader in the field of quantum computing. In fact, I met him, I think, pre-pandemic in one of the quantum computing conference that he was sitting, in fact, right next to me. So it was a very nice, event to get to know more experts in the field. So Scott's research covers a wide spectrum of topics related to computer science. They include high-performance computing, programming modeling, applications of performance analysis, including average efficiency, high-speed communication, and many others. And he has been recently beginning to investigate quantum computing, and is currently leading a few very exciting research efforts related to both circuit-based quantum computing and also quantum annealers. So Scott has the graduate degrees, PhD and MS both in computer science from University of Illinois Urbana-Champaign, and he has a bachelor's degree in mathematics and computer science from Carnegie Mellon University, which is very good because I also did my PhD from Carnegie Mellon, so somehow we're connected through this. Anyway, so without using too much time, let me give the floor to Scott. Thank you very much for joining us today, and we definitely look forward to your presentation.
All right, thank you for that introduction, Professor Yu. So the title of my talk is Running Classical Programs on a Quantum Annealer. And I'm actually not going to be talking about the quantum or the quantum annealing part for about 20 minutes. Instead, I'm going to be talking about monkeys. So let's imagine we've trained a monkey to turn a light on and off. We've also trained this monkey to understand 4 instructions. We could tell the monkey that I want this particular light to be turned on. I want this particular light to be turned off. I want these 2 lights to be in the same position, either both on or both off, or I want these 2 lights to be in different positions, either on, off, or off, on. Our monkey loves bananas, so we're going to give him 1 banana for every instruction he obeys correctly. Okay, so here's an example of a set of instructions we could give the monkey. We could say, here's 3 lights, A, B, and C, and we tell the monkey, I want light A to be on, I want lights A and B to be in the same position, and I want lights B and C to be in different positions. So the monkey can think about this, and he might say that he sees the first rule, A should be on, so he could turn on light A. We want lights A and B to be in the same position. They're currently different, but if he turns on light B, now lights A and B are in the same position. And we want lights B and C to be in different positions, and they already are. We have an on and an off. So the monkey has honored all 3 rules, and we give the monkey 3 bananas as his reward. However, it's not always possible for the monkey to honor all of the instructions he's given. For example, if we tell the monkey, I want lights A and B to be in different positions, I want lights B and C to be in different positions, and I want lights C and A to be in different positions, this poses a problem for the monkey. He could turn on light B, for example. In that case, rule 1 is honored, A and B are different. Rule 2 is honored, B and C are different. But rule 3 is violated. C and A are the same, even though we wanted them different. And no matter how the monkey tries to configure the lights, the best he could do is to honor 2 of the rules, and 1 of the rules will not be honored. So the best the monkey can get in this case is only 2 bananas. So now we're going to teach our monkey some graph theory. There's a problem in graph theory called max cut, for the maximum cut of a graph. The idea is you have a graph, a set of vertices connected by edges, and you want to color the vertices in one of 2 colors, say red and blue, to make it as hard as possible to cut the graph into 2 partitions, a red partition and a blue partition. Here's what I mean by that. So in this particular graph shown here, let's say we color A, B, and D blue and C and E red. If we want to cut this graph into blue and red vertices, we have to cut through 3 edges. So we say that the size of the cut between ABD and CE the blue and the red partitions is of size 3. So let's see if we could teach our monkey to beat that score of 3. And the first observation is, if you look at the green edges, the edges that are cut, they all connect a blue vertex and a red vertex. The vertices that are left alone are those that connect blue, blue, and red, red. So what we need to do to maximize the number of edges that have to be cut is the same as maximizing the number of edges whose adjacent vertices have different colors. So to put this into monkey language, we'll use on and off lights instead of red and blue, because that's what the monkey understands. And now what we'll tell the monkey is, for each pair of connected vertices, we want them to be different in terms of on and off. So we'll tell the monkey, I want A and B to be different. I want A and C to be different. I want B and C to be different. I want B and D to be different. I want C and E to be different. And I want D and E to be different. So the monkey thinks and thinks how he can get as many bananas as possible. And what he comes up with is turning off A, B, and E, thereby putting them in the blue partition, and turning on C and D, thereby putting them in the red partition. So in this case, A and B are not different, but all 5 of the remaining rules are honored. So the monkey will receive a reward of 5 bananas. And as you could see, partitioning this graph into a red partition and a blue partition requires a cut of size 5 to put all the blues separate from the reds. And it turns out that's the best you could possibly do for this particular graph. Now we're going to keep the rules the same. So the monkey still understands, I want this light on, I want this light off, I want these 2 lights to be the same, or I want these 2 lights to be different. But we're going to, instead of always giving him 1 banana for getting an instruction correctly executed, each instruction will carry a reward with it of how many bananas the monkey will get if he follows that instruction. In addition, if there's an instruction the monkey fails to honor, we take away that many bananas from the monkey's accumulated stash. So how should the monkey handle the following set of instructions? If he turns on light A, he receives 1 banana. If he turns on light B, he receives 1 banana. If he turns off light C, he'll gain 2 bananas. If A and B are different, he gains 1 banana. If A and C are the same, he gains 2 bananas. And if B and C are the same, he gains 2 bananas. So I realize that's difficult to do in your head. So let's actually work out all of the possibilities. There's 3 lights, so there are 2 to the 3rd, or 8 possibilities. And as you could see from the chart on the right, he gets different rewards for each combination. In the first row, where we have off, 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 the monkey will does not have light A on, so he'll lose 1 banana. Does not have B on, so he'll lose another banana. But he did turn off light C, so he gains 2 bananas. A and B are not different, so he loses a banana. A and C are the same, so he gains 2 bananas. B and C are the same, so he gains 2 bananas. And when you add that all up, it comes out to a total of 3 bananas. The next row is really the worst the monkey could do. If he has off, off, on, that violates all the instructions, and we take away 9 bananas from the monkey's storehold of bananas. The next row with just B is on, the monkey gains 3 bananas. The next row of B and C are on, the monkey loses 1 banana, and so forth down the list. So there's a pattern to this. You'll notice that the best the monkey could do is gain 3 bananas, and there's 3 ways he could do that. So we have a 4-way tie at best for 3 bananas apiece, and those occur at off, 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 on, off, on, off, off, and on, on. And that's if you think of off as false and on as true, that's a logical conjunction. We're saying that C is on if and only if A and B are both on. So from computer engineering notation, we taught our monkey an AND gate, which is notated with this D-shaped green symbol in the middle. So A and B feed in, and what comes out if A and B are both on is C being on. Now we already have a NOT gate, which is implemented just with the single instruction, I want A to be different. That's shown by this blue triangle. And a wire is just another way of telling the monkey, I want A and B to be the same. So we have the start of a hardware circuit design. And this goes further. We could, in fact, teach our monkey any digital gate. So an OR gate looks a lot like an AND gate. We just switch the sense of the first three rules from on, off to off, on, and keep everything else the same. And in this case, light C is turned on if either A or B or both are on. So the monkey gets the most rewards for off, on, off, on, and on. This orange notation at the bottom shows the standard notation for an OR gate in digital logic, that if A or B or both are on, then C is on. A nice property is that the rules we give the monkey are additive. So at the bottom of the screen, you see a circuit in which E is on if D is on or both A and B are on. So all we need to do is take the rules we had computed already for and the rules we had computed already for OR and give that complete set to the monkey. The rewards or punishments add up also. If you look at rules 3 and 7, for example, rule 3 says that if the monkey turns off light C, he gains 2 bananas. Rule 7 says if the monkey turns off light C, he gains 1 banana. So if the monkey does indeed turn off light C, he'll get 2 + 1 or 3 bananas for following those instructions. So let's talk a bit about how hardware design works. Nowadays, nobody lays out a computer processor or any complicated circuit gate by gate. It would be way too tedious to do that. Instead, developers rely on what's called hardware description languages. These look more or less like an ordinary programming language in that they have variables, arithmetic and relational operators, conditionals, loops, and modules. A special compiler called a hardware synthesis tool compiles programs written in these hardware description languages to a set of logic primitives, such as and, or, not, and others. And they often perform a variety of optimizations to reduce the amount of logic that's required. Here on the lower left of the screen, you see an example program written in Verilog, which is a hardware description language that's been around since the 1980s. The way to read it is we're defining a module called example that takes 3 1-bit inputs, A, B, and C. It produces a single 1-bit output called D, and D is computed as A and B or not C. So when you run this through the hardware synthesis tool, it produces the circuit you see on the lower right, where we compute A and B or not C. So what this means is that we no longer have to figure out how to manually prepare instructions for our monkey. We figured out how to do and or and not, but now we could leverage those. And instead of having to convert every problem individually to a set of monkey instructions, we could write code in a hardware description language. We could then synthesize that code to a digital circuit. Then for each of the gates in that digital circuit, we already have a set of instructions for a monkey, and we just combine them in the appropriate ordering and with the correct variable assignments and hand that to the monkey, and the monkey can now execute the program which inverted to instructions that the monkey understands. Here's a more sophisticated example. Validating a map coloring. So the idea is you have a map. Here I show a map of Australia. And the goal is to determine if a coloring is valid. A coloring is valid if you use at most 4 colors and no 2 adjacent regions are colored with the same color. So in this case, we want to write a program so that given a coloring such as this, the program will output true because there are 4 or fewer colors and no 2 adjacent regions use the same color. It does not take very much code to write such a program. Here's what it looks like in Prolog. The way to read this is that we have, for each region, New South Wales, Queensland, South Australia, and so forth, we have a 2-bit input. And the reason we have a 2-bit input is that there are 4 colors, and 2 to 2 bits is 4 possible colors. And we're going to output a single bit called, and the way valid is computed is if Western Australia is not equal to Northern Territory, and Western Australia is not equal to South Australia, and North Territory is not equal to South Australia, and so forth, then this is a valid coloring. So that's all it takes to determine if a particular map is correctly colored. Now, a point I want to make about the monkey instructions is that they represent relations, not functions. So even though I've been presenting them essentially as functions, like an and or an or, where it takes inputs and produces an output, the lights are not predefined to be inputs or outputs. We give the monkey a set of lights, and he has to figure out which ones to turn on and which to turn off based on the rewards. If we want the monkey to teach a combination of lights as a function, where we specify certain lights as inputs and certain as outputs, we could tell the monkey that for the inputs, we'll give him lots and lots of bananas if he gets those correct. For example, if we just focus on our AND gate, and we want the monkey to tell us what is the value of true and false. So to do that, if we say the first value is A and the second is B and the output is C, we really want the monkey to set A to true and B to false. So here we could take our AND instructions and we increase the rewards for A and B to be 10 bananas apiece. So 10 bananas for turning on light A, making it true, 10 bananas for turning off light B, making it false. And then we want to see what combination the monkey comes up with, in particular, what he chooses for C. In this case, he comes up with on off, which is what we wanted, and the value of C is off, which is a statement, true and false. They're not both true, so the result is false, and C is correctly off, which is false. And this happens to be worth 23 bananas. What's really neat, though, is we could run the program backward. We could specify an output by offering our monkey lots of bananas. So for an AND gate, what inputs produce an output of true? So what A and B give us A and B is equal to true. So we follow the same pattern we just did. Here we leave everything alone from the original AND, but we're going to give the monkey 10 bananas if he turns on light C, because we really want the output of this AND gate to be true. In this case, the monkey thinks, and the best he could do is on, which is, again, a true statement. True and true is equal to true. And in this case, that happens to be worth 15 bananas. But here's something to think about. What if we give the monkey an unsolvable problem? If we said, what value of B would we have if false and B is equal to true? Well, there is no value of B that makes that a true statement, because false and anything is equal to false. So let's follow the process we've been using. We start with the basic AND set of instructions. but we give the monkey 10 bananas to make A false. We leave B alone because that's what we're solving for. And we give the monkey 10 bananas to turn on light C because we want the output to be true. And the monkey will then give us the output false, true, true, which happens to be worth 22 bananas. So that might be a bit puzzling because false and true is not equal to true. This is not a correct statement. Why didn't the monkey just shrug his shoulders and say, sorry, I can't solve it? The reason is that the monkey just goes strictly by the set of bananas he gets as a reward. So no matter how he sets the lights, there will be some reward associated with that. In this case, you look at the 8 possibilities, and there's always a best solution. In this case, off, on happens to be the best solution. The monkey has no knowledge about that we're trying to solve a logic problem. All the monkey knows is that he's trying to get as many bananas as possible, and this is the configuration that gives him the most bananas. There's no way to say no solution could be found. It's strictly a matter of finding the best solution that he can. Now I'm going to digress for a bit and give you a quick introduction to theoretical computer science. Here on the right, I have some pseudocode, which is doing a matrix multiplication. It takes 2 n by n matrices A and B, and it's going to multiply them to produce a third n by n matrix C. And suppose I asked you, how long does that program take to run? Well, the correct answer is it depends. It depends on how expressive the programming language is that you write this in, because that determines in part how efficient the compiler and interpreter can be in mapping that to the underlying hardware. It matters how fast your hardware is and how many things the hardware can do at once. And of course, it matters what the value of n is. A larger n will take longer than a smaller n. Computer scientists abstract all of these issues away. And when they think about time, they think about it in terms of the amount of work that has to be done as a function of the input size. In this case, there's just one input, which is n. So as n grows, the number of operations this particular program performs grows proportionally to n cubed. The reason is the first for loop executes n times. For each of those n iterations, the second loop executes n times. For each of those total n squared so far iterations, the third loop executes n times. So therefore, the inner body, the last line of this pseudocode, where we're doing multiplication and addition and assignment, that's going to execute a number of times proportional to n cubed. So we'd say that this program runs in n cubed time. Computer scientists care a lot about classifying problems by the minimum amount of work that has to be performed in the worst case to solve them. Programs that run in a polynomial time are considered easy, which means that if you have n inputs, that requires n to the k amount of work for some k. So n units of work, n squared units of work, n cubed units of work. Anything more than polynomial time, super polynomial time, is considered hard problems, where, for example, exponential time is an example of super polynomial. So n inputs, in that case, would require k to the n units of work, 2 to the n, 3 to the n, 4 to the n. So those are difficult problems. Here's a quick graph to convey what those look like. If you see problem size on the x-axis and time, really the number of operations on the y-axis, a polynomial time function grows slowly and smoothly, while a super polynomial function skyrockets upward. A point to note is that for small input sizes, it's possible that a super polynomial time program might even run faster. But what we care about is the limit. As problem size gets bigger and bigger and bigger, at some point there will be a crossover, and we could say that the super polynomial algorithms will take longer than the polynomial algorithms. So now let's consider specifically decision problems, problems that you could answer with a yes or a no. So computer scientists have categories for these. P is the class of easy decision problems, questions you could answer yes or no in polynomial time. For example, if I gave you matrices A, B, and C and asked, is C the correct product of A and B, you could compute that in polynomial time. You could multiply A and B yourself, which, as we saw earlier, takes n cubed time. Then you could compare that to the matrix C you were given, which would take n squared time. And the result is a polynomial, n cubed plus n squared. So that's an easy problem. The class NP are problems that are at least as hard as P. Those are problems in which you could verify a given solution in polynomial time. For example, coloring a map with k colors is not something that could be done in the general case in polynomial time. But if I gave you a map and is this a correct solution, you could check that each region has one of 4 colors, or k colors in this case, and that no 2 adjacent regions have the same color, and that only takes polynomial time. You just loop over each of the regions and each of its neighbors. So that's a problem that's in the class NP for non-deterministic in polynomial time. Because these tend to be difficult problems, the 2 ways that one could solve them are either a brute force examination of all possible solutions, which could be exponential in many cases. Typically, that's easy to program. You loop over each possibility, you check if it's valid, and output it if it is. But it could run very slowly because there might be such an enormous number of possible solutions, even for a modest number of inputs. So what people who care about the performance normally do is a heuristic approximation, which the approach is to map the problem to another problem for which you have a guess for, and then map the results back. So you're coming up with essentially a very good guess. This runs fast, but it's typically difficult to program. It's not always obvious how to map the problem you want to solve to a problem for which someone has already developed a heuristic solution, and how to map the solution back. And furthermore, by virtue of the name heuristic approximation, it's not guaranteed to give a correct answer. It'll usually give you a correct answer, and typically that's good enough. So here's an example of a problem that's in NP. We go back to our map coloring, but now we turn the problem around. We want to find the colors of the map using at most 4 colors, such that no 2 adjacent regions have the same color. So this is much more difficult than verifying that a given solution is correct. But what's interesting is, if we start with the same program we write before that validates a coloring, what we could do is, as we convert this to a circuit and convert that to monkey instructions, we could offer the monkey a lot of bananas if valid is true. So we're telling the monkey we really want this to be a correct coloring, and then the monkey will choose colors that lead to it being a correct coloring. So we tell the monkey we want this to be true, and the way the monkey can get the best number of bananas is by choosing a coloring such that no 2 adjacent regions have the same color, because it honors the most constraints in that assignment of valid. So we got the monkey to solve one difficult problem. Here are some additional examples of problems that are in NP that the monkey can solve. A classic one is called circuit satisfiability, which asks what inputs, if any, to a given digital circuit produce an output of true. So given some digital circuit, we could convert that to Verilog code in a fairly straightforward way. We offer the monkey a lot of bananas if it outputs true, and we see what he comes up with for the inputs. However, we have to sanity check the solution because there's a possibility that none of the inputs, no organization of inputs will return true. And remember what we saw before with the impossible and example. The monkey always returns a solution, whatever maximizes the number of bananas he gets, without considering, is this mapping what we think of as inputs to what we think of as outputs. Fortunately, checking the solution to this sort of problem can be done quickly, again, meaning in polynomial time. Another problem monkey can solve is integer factorization. So given an integer, we could ask, what are the two prime factors, assuming that's a semi-prime, meaning that it has exactly two prime factors. So the code for that, we just write a multiplication. We say that a product is produced by multiplying a multiplicand and a multiplier. In observing that if you run a multiplication backward from the product to the multiplicand and multiplier, that's how you do factorization. So we offer our monkey lots of bananas if the product is what we want it to be, the number that we want to factor, expressed in base 2. And then the way the monkey gets the most bananas is by choosing a multiplicand and multiplier that multiply together to produce that particular factor, that product. Okay, so what we've seen so far is that it's not obvious how we could instruct our monkey to do things in terms of his 4 rules. Turn on this light, turn off this light, make these 2 lights the same, make these 2 lights different. Because we have to figure out the correct balance of rewards and punishments individually for each problem. But once we've solved that for a very restricted subset of problems, logic gates, so and or and not and similar things, then this enables us to use a easy to program in hardware description language. And from that, we could produce circuits. And from that, we could produce monkey instructions. But a question that I pondered was, can we do even better? Not very many people know digital circuit design. Is there a high-level language that lends itself to translation to monkey instructions? So I thought about this a bit, and the first language that came to mind is a language called Prolog. This stands for, in the original French, programmation en logique, or in English, programming in logic. It's a language that's been around since the early 1970s. It's based on a branch of predicate logic called horn clauses, which makes it very different from programming in, say, Python or C++. It was initially promoted for use in symbolic artificial intelligence, and it was used quite extensively in Japan for about 10 years. But beyond that, it never really caught on. So it's often mentioned in an introductory programming languages class and promptly forgotten. Let's take a look at some sample Prolog code. In the upper right, you see really the 3 main things that Prolog supports: facts, rules, and goals. The first line is a fact where we're asserting that monkeys like bananas. The next 2 lines are a rule that say hyenas like X if monkeys like X. So variables in Prolog start with capital letters and symbols start with lowercase. So in other words, we're saying hyenas like whatever monkeys like. The final line of this program is a goal, which asks, what do hyenas like? So the Prolog system has a proof engine, and it's trying to solve for variables in the goal. So in this case, for what? Technically, it's trying to disprove the claim that there is no value that can be assigned to what, but that's a technicality. So the control flow is, the Prolog says, I have to find what do hyenas like. So the first predicate in the program, that monkeys like bananas, is not yet helpful. But the next 2 lines are, because it says, if I could show that monkeys like something, then I know that hyenas like that. So then it digs deeper and says, can I say thing about what monkeys like. It sees the first statement in the program, the first predicate. It says, monkeys like bananas. So I could prove that monkeys like bananas. Therefore, if X is bananas, then I know that because monkeys like bananas, hyenas therefore like bananas, and therefore what is equal to bananas. So it is solved for the variables in this program. Unification is what we call that concept of assigning values to variables to make these patterns match. Here's another program where it names 2 people as male, 2 as female. It says what company everybody works at, and then defines a rule that says 2 people know each other if they both work at the same company, C. So if we gave it a goal that says A knows B, A is female, and B is male, Prolog could say that A is Victoria, B is Alan, and internally to figure that out, it would have determined that C is D-Wave, that both Alan and Victoria work at D-Wave, and therefore they both know each other. But if we give it a goal of who does Marcus know, Prolog would fail to assign anything to W because it has no rules that tell it anything about Marcus. These predicates can complete 0, 1, or more times, where Prolog returns all the valid variable assignments. So if we asked it who knows whom, literally A knows B, it would say Victoria knows Alan, but it would also say Alan knows Victoria, because both cases they work at the same company. It would also return stupid things like Alan knows Alan, Victoria knows Victoria, Chad knows Chad, and Talia knows Talia, because in all those cases, the 2 names work at the same company. If there are no variables in the goal, Prolog will return true if the goal is provably true, or false if it is not provably true. So if we ask Talia works at IBM, Prolog would say true. But if we stated Talia works at D-Wave, Prolog would return false because it has no information about that. What I managed to do was to automatically convert from Prolog to Verilog. So in taking the code from the previous slide, this program written in Verilog first defines a number associated with each symbol, because when we have a digital circuit, we need to work with numbers. Then it defines another module for the query we have, the goal. So this says A knows B, A is female, B is male, and says that the result is valid if those are honored. We define a rule for A knows B, and if that's a valid statement, if A is male, female, 2 people work at the same company. The key idea here, as we've seen in all the previous examples, these modules all return a valid bit if the results are honored. And you can see how this is going to work. You could take a Prolog program and compile it to Verilog and compile that to a circuit, and from that to monkey instructions. As before, we give the monkey lots of bananas if valid is true, and then the monkey will solve for all of the things we haven't pinned down with a huge banana reward to give us the values of all of those variables. So now we can take this very high-level predicate logic Prolog and write programs in that and manage to convert it to something the monkey understands. In this particular case, the code translates to 293 monkey instructions, more than I could fit on a slide. But the great thing is all we had to do was write that little snippet of predicate logic code and convert it to Verilog, to circuit, to monkey instructions, and the monkey knows how to follow them. So all this time I've been talking about this monkey. I'm ready to see a photograph of this monkey we've been talking about. Well, here it is. Now, I realize that's probably not what you were expecting to see as a photograph of a monkey, so let me explain. What this talk has really been about is quantum annealing. So this is a picture of a D-Wave Advantage, a quantum annealer produced by a Canadian company called D-Wave Systems. It's a special purpose computer that uses quantum effects to solve a particular type of optimization problem. What that optimization problem looks like is as follows. It's a quadratic expression where we're trying to find the sigmas that minimize this expression. So the first term, the sum of the h's times the sigmas, is then added to a double sum of two sigmas, so it's a quadratic. You provide the h's and j's, those are real numbers, and the hardware will heuristically solve for the sigmas, which are Booleans, although typically they're expressed as -1 and +1 instead of 0 and 1. By heuristic, I mean there's no guarantee that the solution is correct, and there's no guarantee that the same solution will be returned across multiple runs. And that's it. A program is a list of numbers, of real numbers, and the output is a list of Booleans. So it doesn't sound like much, but this is interesting because of the size of n, which could be, on the current hardware, as big as 5,760, which means that the number of combinations you'd have to consider to find the best solution can be as large as 2 to that power, which is an incomprehensibly large number. And yet the system can return a solution heuristically in as little as 1/1,000,000th of a second. Well, how is that possible? So imagine you're trying to find the sigma values that minimize a high dimensional function, a 5,760 dimensional function that has 5,760 sigma variables. So the approach is something called quantum annealing. Now, I don't know how to present a 5,760 dimensional function on a slide. So for presentation purposes, I'll show you just a one-dimensional function. So here we have some arbitrary one-dimensional function. It takes as input sigma and returns some function of that. We want to find the sigma that minimizes the height of this function. So the way that quantum annealing works, instead of starting with the problem you want to solve, you start with a known trivial problem, say one that looks like this. And the way we're going to find it, if you're familiar with simulated annealing, it's a very similar process. If not, imagine that we're going to roll a ball down this hill, and where the ball settles down, that's going to be the minimum value, the lowest point. Now, the way quantum annealing works is we start with the ball in the solution state. We start with this trivial problem. And the cool thing is we gradually change the problem from the trivial problem to the problem that we actually want to solve. And there's a theorem in physics that says if you make this change slowly enough, then if you start in a solution, you'll wind up in a solution. Under the covers, quantum effects are used to make this happen. The key mechanism is something called quantum tunneling, which means as the ball rolls around, if it gets stuck in a valley that's not the minimum valley, it could cut through a hill as long as it's not too wide, but regardless of how tall it is, to get to the next valley. So it could hop from valley to valley, and with a higher probability than you could classically find an optimal solution. The funny thing about quantum annealing is that execution time is an input. In theory, the slower you anneal, the more likely you are to find a correct solution. In practice, if you run too long, that opens up vulnerability to defects caused by stray particles hitting the computer. On a D-wave advantage, the annealing time lies in the range from 1 microsecond to 2 milliseconds, which is fast enough that you typically don't just run once, you run a large number of times. This on a current system could be from 1,500 to 3 million times. You get some statistics and you assume that the results that occur the most are the most likely to be the correct ones. So let's interpret the optimization problem a little slower. So if we say that sigma of +1 is true and -1 is false, and we look at some of the possibilities. So let's say h is -5. So the product can be +5 or -5. And the way to have sigma be to have the product be the smallest, in this case -5, is for sigma to be +1. So the D-wave in case would favor +1. If h is 0, then the product is 0. And if h is positive, say arbitrarily making it plus 5, then plus 5 times minus 1 is minus 5, plus 5 times plus 1 is plus 5. Minus 5 is smaller, so the d-wave would return minus 1. In other words, negative h says, I want sigma to be true. 0 says, I don't care if it's true or false. And positive says, I want the sigma to be false. If you look at the quadratic terms, we have a similar pattern. We now have 4 possibilities instead of 2. So if j is negative, then you get the smallest product by the 2 sigmas being equal, minus 1 or plus 1, because that gives you a positive times a negative. If j is 0, then you get all zeros, and it doesn't matter what you choose for sigmas. And if j is positive, then the way to minimize a positive times 2 values is if they're different, because that gives you a negative and a positive, which is a negative. Multiply that by a positive, you get a negative. So positive j says, I want these 2 values to be different. So I hope you figured out the connection by now, that the reason I said the d-wave is the photograph of the monkey is because they're doing the same thing. The number of bananas the monkey gets is the same as this function that the d-wave is solving, except the minus sign. The d-wave is trying to minimize the function, and the monkey is trying to maximize the number of bananas he gets. But the rules are the same. A negative h is the same as I want this light bulb on. Positive h is saying I want this light bulb off. Negative j is saying I want these light bulbs to be equal. And the positive j says I want these light bulbs to be different. So example, the AND gate again. The magnitude of the coefficients is the number of bananas the monkey gets. And the sign is if we want the light to be on or off for the linear terms, or same or different for the quadratic terms. So now I'm going to tell you about some new work I've been doing. This is brand new. I'm very interested in programming models. And the question I've posed is, can we define a new programming model from which you could compile code for quantum annealers, for classical computers, and for general purpose quantum computers, all from a single source program. Write a program once and run it on this wildly different hardware. So I haven't talked about general purpose quantum computers, so let me do that. A program for a universal quantum computer, specifically a circuit model quantum computer, is a matrix product of matrix tensor products of unitary matrices. So that's a bit of a mouthful. So let me give you a concrete example. Here we have 3 2x2 matrices that are multiplied together with a tensor product, which means for each element of the first matrix, you multiply it by each element of the next matrix, and so on. So here, because we have 3 2x2 matrices, it's for all of the first, for all of the second, for all of the third, would produce an 8x8 matrix. The green matrix in the middle is just another given 8x8 matrix. And the way you run a program is by feeding in a vector of the appropriate size, in this case, 8 elements, and you get out an 8-element vector. In practice, because there's so many matrices that are used over and over again, there are names assigned to them, and they're looked at as being very much like a digital circuit. So that preceding set of matrices would normally be written as 3 bits, really qubits, come in. The first 2 are run through what's called a Hadamard gate, H gate. Then the green is what's controlled NOT gate, and you get as a result a vector which can be interpreted as a superposition of 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. And if you're astute, you might notice that that's, once again, the AND gate we've been using throughout this talk, that we're feeding in 3 lights that are off, and what comes out is off, 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 on, off, off, or on. So how can we write a program that targets such wildly different computational models? What I've come up with so far is something I'm calling n choose k, where there's a single primitive that says, given n inputs that are Boolean, I want to force k of them to be true. So here's a case you see where I've said I want one of A, B, C, and D to be true, and it does what you would expect. One of those will be true. If I change the 1 to a 1 or 3, that says exactly one of A, B, C, and D must be true, or exactly 3 must be true. So it would look like these possibilities. Another thing that you could do is the variables don't have to be unique. So you could represent an AND gate by plugging C twice into one of these boxes that says 0, 1, or 4 have to be true. If you look at the possibilities, the first line, 0 of them are true. The second, B is true, 1, that's a possibility. The third line, 1 of them is on, 1 is a possibility. But if we tried to turn on C, because C counts twice, both C's have to be on. 2 is not one of the allowed numbers. So we have to go all the way up to 4 by turning on A and B, and that gives us our AND gate when you look at A, B, and one of the C's. A final concept is that variables can be shared across those blocks. So to solve map coloring, all I could fit on the slide was 2 regions, let's say New South Wales and Queensland. So here we have 8 statements that we have to assign trues to, either true or false, that New South Wales is red, it's yellow, green, blue, Queensland is red, yellow, green, blue. So to start, we could have a box where New South Wales is red and Queensland is red. You have to choose either neither of those to be true, meaning neither is red, or one of them is true, but you can't have both of them are true because they're adjacent regions. We said only 0 or 1. And we do likewise for the other regions. This isn't sufficient because you could choose in all cases false, that no region has any color. So we have to add another box that says one of New South Wales is red, is yellow, is green, or blue has to be true, and likewise for Queensland. So now each region has to have exactly one color, and the 2 regions have to have a different color from each other. So nChoose provides a superset of what we can instruct our monkey. We told the monkey initially, I want light A to be on, which means 1 out of 1 light should be on. A and B should be in the same position, saying either 0 or 2 lights should be the same, should be on. And B and C to be different is another way of saying 1 out of these 2 should be on. We could go the other direction also. We could say, here's a block where we say 1 of A, B, and C should be on, and it's possible to produce a set of monkey instructions that correspond to that particular nChoose block. So my hypotheses are that this model is rich enough to express a variety of computational problems, and that these programs can be mapped to quantum annealers, to universal quantum computers, and classical computers. But this is a very new research effort. I can't prove any of those hypotheses yet, so stay tuned for future developments on this front. To summarize my talk, a quantum annealer heuristically solves a specific minimization problem where you provide the real valued H and J coefficients, and the system will solve for the sigmas, which are Booleans. But this can require a fair amount of creativity to figure out how to map a problem to that form. So my proposal is that if you could solve a few simple constraint problems and then map classical programming languages like Prolog and Verilog, and eventually this nChoose into that form, then you have something that can be fed to a quantum annealer. The unique attribute is that the resulting programs represent a relation of inputs and outputs, which means that you could, unlike a conventional classical program, you don't have to run it from inputs to outputs. You could also run it from outputs to inputs, effectively running it backward. And the reason that's important, tying it back to the digression I had on computer science and NP problems, remember that to solve these difficult problems, you either have something that's slow but easy to program, or fast but hard to program. And the approach that I've proposed in this talk is sort of a best of both worlds. It's easy to program and it runs fast. So you write your solution verifier in Prolog or Verilog, and you run it backward from this is a correct solution to the correct solution. The only con is it's still not guaranteed to give a correct answer. It's a heuristic approximation. So in summary, my goal, the goal of my research is let's make programming quantum computers simple enough that a monkey can do it. And with that, I hope that we still have some time for questions, and I'll let Professor Yu field those, I guess.
Thank you so much, Pakin. Dr. Pakin. This is a very nice presentation. Thank you. So now I think now the floor is open for questions and comments. Is there any question from the...
If I may?
Please.
Yeah, thank you. Yeah, thanks very much. That was really fun. I'm curious what would happen with the I think it was 5,700 bits or something. That seems quite small when one thinks about just sort of general inputs. Is that a constraint? And are there ways to sort of break down complex tasks that require more to that size?
Yeah, that's a really good question. That is, in fact, a really huge constraint because even though 5,000 is orders of magnitude more than the universal quantum computers, which are barely at 100 yet, it really does mean that your program takes as input 5,000 bits and produces as output 5,000 bits. And yeah, there aren't a lot of, it's hard to find problems that do so much compute that they can work on such a tiny amount of input and output. It's a terrible performance bottleneck. Up to this point, the machines are largely used for solving toy problems, technology demonstrations. People have looked at ways to split larger problems into pieces, but it doesn't work very well because the glue to put together those pieces typically has an exponential cost. So if you split into two pieces, maybe you could tolerate that. But if you had a really big problem and you split it into 10 or 100 pieces, then you would lose pretty much all the benefit of the quantum annealer. So that is a big issue, and people are working very hard at how to scale these up, but it's a very challenging problem.
Thank you.
Great. Any other question for Dr. Pakin?
Yeah, I had a question.
Please.
First of all, that was a great talk. I have been convinced that quantum annealers have a future, and they're not going to be completely taken over by other models of computing, of quantum computing. One thing that does concern me a little is that, well, first, I really like the n choose k boxes idea. I'm just a little concerned that maybe if your n is like a large number, then your representation of those bits might be far away from each other. And then it might be hard to connect two bits that are far away in a quantum annealer. So do you have any thoughts on that?
Yeah, so that is an issue that as you do the mapping to the hardware does have a specific physical topology. And the good thing is that you could provide hints to the mapper and say, because I know this is coming from this n choose k block, I want you to try hard to keep these close together. It won't always be possible. The latest generation of D-Wave's hardware has enriched the topology where it's a higher degree graph. So more qubits will be closer to each other than in prior generations. So the good thing about something like n choose k is the ability to provide those hints to the hardware and tell it, try hard to keep this block close to each other, try to keep this block close to each other, but those separate blocks, it's okay if they're a little far apart. The problem with them being far apart is it costs qubits to logically bring them close together. So you pay in terms of qubits, and you also pay in terms of reliability. You're less likely to get the correct answer the more hops you have to take to produce these virtual qubits that are made by distant physical qubits. So I'm hoping that n choose k will help with the problem, but it can't make it go away completely.
All right, thanks.
Great. Any other question?
Sorry, one more, if I may. You mentioned that the quantum annealer is less likely to return an optimal solution if you have widely separated values. Is there any way to know from the input to the integer program whether it has that feature?
Not a priori. So if you worked out all of the possibilities, you could figure it out, but that's begging the question. So there's not in the general case a way to know. One thing that helps is in the approaches that I presented here, when you're breaking up a problem into these little known problems, you could work out the cases for each of those known problems. The quick way to do it is to look at what's called the gap, which is the difference between the value of the correct solution and the first incorrect solution. Or monkey talk, how many bananas he gets in the best case versus the second best case. The bigger the gap, the more robust the solution is likely to be. In reality, it doesn't actually go by the final values in a quantum annealer. It goes by what happens as the anneal proceeds. And that's very computationally expensive to figure out, but it is mathematically possible to come up with that. So the short answer to your question is there's no good way to do it. The slightly longer answer is there's a way to guess, and the full answer is it can be worked out exactly, but you wouldn't want to because it's too expensive.
Got it. Thank you. And that situation that you described where it's less reliable is actually one where maybe practically you don't care so much. Like if the gap is small and you end up with one of those sort of solutions that's just a little ways away from the optimal, at least in my world, that's pretty good.
Oh yeah, so that's what D-Wave is betting on. So they really formed their whole company around that exact thought that they said with the universal quantum computers, those are like a conventional computer that are digital and you get the correct answer or you get a wrong answer. And they said, we know that there's going to be errors. We know we're not going to get correct answers in many, many years because the technology, the engineering is not there yet. But if you're solving an optimization problem, then yeah, getting a good solution or maybe many good solutions quickly could be more valuable than getting the perfect solution in a long, long time. So that is their corporate philosophy and why they went with quantum annealing, where everybody else is going with general purpose quantum computing.
Cool. Thank you very much. That helps. Yeah.
Thank you. So maybe just a quick follow-up question. What's your outlook for this whole industry in the next 10 years, let's say? Do you think annealers would exist for a long time? Because, there's some discussions going on right now in terms of, these annealers based versus the game models. Also, do you expect at some point, we could operate these quantum computers just like what we are doing right now for the classic ones, that we don't need to deal with these heuristics and all these probabilistic natures of the solutions?
Mm-hmm. Yeah, I've thought about that quite a bit. And what's formed in my head is the distinction between quantum annealer and a general purpose quantum computer is sort of like the difference today between a decent calculator and a really awful computer. So which is better? And there's not a single answer to that question. If you need an answer today, you'd probably go with the decent calculator rather than the broken computer. But if you look to the future, you know that the bad computers aren't going to be bad forever. And at some point, they'll surpass the calculator. At some point, you know that the computers are going to be better than the calculator. So we're not there yet, but it seems to me like that crossover is inevitable. So who knows how many years that will take. There's a lot of very difficult engineering that's going into that, but it seems like the annealers eventually will go away. But in the short term, I think they provide a very valuable niche that they could do this optimization problem. They could tolerate the noise in an elegant way and give you some results. And that might be better than a general purpose system that pretty much always gives you the wrong results.
Great. Thank you so much, Scott. So any last minute question? I know we are running a little bit out of time. So if there's any last minute question, please feel free to unmute and ask. All right. Well, I think it's a good time to conclude now. Thank you so much, Dr. Pakin, for the wonderful presentation and for spending time with us today. In a normal time, we try to share hand with you and then give you assistance and you give back. But now we have to run it virtually, so I would talk to Daniel to ask him to mail the gift back to you directly. Thank you so much again. Really appreciate it.
Yeah, thanks for having me. I enjoyed doing this.
Okay, thank you.